Okay, hello everyone. My name is Fabrizio and is Daniele from 20 Squares, and today we are going to talk about compositional game theory. That is basically, the kind of bread and butter we use 20 Squares to do mechanism design based analysis of protocols and stuff like that. So basically, the kind of flavor of mechanism design we do is heavily based on this theory that is being developed by a bunch of people. One of them is Jules, that is over there, and other partners of us, academics. It took a long time, 8, 10 years, but now this thing is basically up to a point when it can be used profitably in production. So I just wanted to use this time to give you a sense of, what is that we do and how it works. So I will start with a digression. That is, to really understand what's going on here, one needs to learn to think in terms of systems and processes. So the idea is, a system is something we can transform and act upon. And processes are things that act on systems and transform them. So, for instance, in here we have a very simple system, that is the system number. You can see this as a state that can be, like any integer. And you have this process called add1 that just takes any number on the left and spits out that number plus 1 on the right. So looking at it like this, it looks like, okay, super simple, perfect. The funny thing about processes is that, when you start thinking about it this way, you can basically compose them. So this is a very simple example. You can see that basically add1 spits out something of type number. And it also takes something of type number as input. So you can concatenate them and basically combine them together. And the idea is that you can compose things when their types match. So when the type of the input matches with the type of the output. There is also a very interesting process for basically any system, that is the do-nothing process. So this is what we call, in the mathematical theory, that we use an identity morphism. So basically this means that for each system, you require to have a process that leaves the system unchanged. And obviously, you see that if this process does nothing, which is, by the way, why we don't draw it at all, when you compose any process with the do-nothing process, is just like getting the process you started with. If I say take a number, add 1, and then do nothing, it's just saying add 1 to the number. Okay, so another example. This is basically gravitation. So the idea here is that you have a process that is, a physical system, a bunch of velocities and positions, in this case, about the sun and the earth relative to it. And then you have this process that is evolve. So it basically says, okay, given some initial parameters of this dynamical system, what happens if I let 1 second pass? And this thing will spit out some other numbers. And again, these things can be composed, obviously. I can basically do evolve for any time by concatenating, a discrete steps of evolution if I want to. And obviously I have the, do-nothing process that is evolve for 0 time. So basically, if you are here and you evolve for 0 time, you stay here. You don't evolve, you don't go anywhere. As I said before, you can compose things when types match. So for instance, with the add1, we could compose them with itself because the types match. Add1 spits out something of type number and takes something of type number as input. But like this composition here is clearly unlawful because the idea is this thing was expecting a bunch of positions and velocities, and I'm feeding it with just a number. And obviously, like this thing says, okay, what do I have to do with it? It's like you are not giving me an input that I understand. So you can compose things when types match. Now, The idea of matching types is super important and really somehow changed the face of programming languages in the last years. I don't know how many of you are familiar with functional programming languages, but the whole name of the game there is that you create a complicated but expressive type system that basically doesn't allow you to do things that do not make sense. So if you ever try to program in Haskell or Idris or Agda or these typed programming languages, in the beginning programming feels much harder because everything you do, the compiler just like keeps bitching, say, sorry, I can't compile, I can't do this, I can't do that. But actually, the flip side of it is that you are taking these extra constraints that somehow force you to produce more well-behaved code. So an idea of where you can use type-driven programming in the right way is, imagine that you have a car, and this car needs some gas to run. But in principle, nothing forbids you to just pour water in the gas tank. Like physically, you can do it. This means, in programming language terms, that probably the type of the gas tank is too loose for the kind of task that thing should perform. So basically, you can feed conceptually incorrect input to that type, to that process, and basically make a mess. So the take-home message of this is that having refined type is important, and when you play this game correctly, you can have code that is more reliable. Okay, so where does all these systems and processes stuff live? The underlying mathematical theory that we use is something called category theory. That is, I'm not going to dive into it by all means, but the idea is that category theory is exactly the superglue of mathematics. It's basically the mathematics of how things compose and interact relative to each other. And since a few years ago, officially since 2018, but actually goes a bit more far back, people started getting aware of the fact that category theory could be applied. In the beginning, this thing was just used in the realm of algebraic geometry and hyper complicated mathematics stuff. But now, in the last years, people realize that, hey, we can use these ideas in engineering. We can use these ideas in computer science. We can basically instantiate categorical examples of systems and processes. And the idea is that, again, when you do it properly, when you define a relevant category of processes and systems you care about, the idea is that when you compose things, the semantic value of the things you are composing is preserved. So basically, you cannot compose apples and pears together. The reason why I'm telling you all this, the reason why this is important is because what we do is game theory in an open way where games are conceived as processes that can be composed with each other. And a fundamental question that we have to be very careful about is, if I compose two games, do I still obtain a game? Do I still obtain something that semantically makes sense as a game? And if the answer is no, then there is no hope that this approach is viable, because you could define one little game Lego brick, then you define another, then you put them together, and you don't know what you have. So the reason why this took a long time to develop is that we needed exactly to get the mathematical details right so that we could be sure that what we were doing made sense conceptually. Okay, so now that I talked very briefly about this kind of preview of conceptual excursus of what we are doing, what we rely upon, we can start looking at compositional game theory proper. So, compositional game theory in a nutshell is a formal language for game theoretic reasoning. Is based on these ideas of systems and processes and ultimately category theory, and has been implemented into a software stack. So you can actually use this thing. It's not just a theoretical gadget. You can actually write code using this stuff. Okay, so the idea is that the implementation is useful to model strategic interaction and allows you to analyze models in various ways. It can be interactively, it could be automated tests, it can be integrated with machine learning frameworks and all this kind of stuff. We can probably talk a bit more about that in question time afterwards. Again, the idea, the key innovation of this is compositionality. This idea that you can plug games together. You can compose games together into a bigger game. The reason why this is very important for us is that basically one of the things we do is economic auditing. So someone comes to us with maybe a spec, not even code, and they ask, does my protocol make sense economically? Or I don't know, can you provide me in the market boundaries within which the market has interest in, I don't know, like defending the peg of my stablecoin. And then the problem is that when you work with projects so early in the product development cycle, their spec changes a lot. So having little game Lego bricks allows us to do quick prototypation, because if you change one thing in your protocol, I can hopefully only change that little game brick in the whole complex game, provided that the types around it stay the same, and I don't have to redo the whole thing from scratch. So that saves time, and it allows us to follow along with the project developing team as they go. And then the idea is, when you go so early in the product cycle, development cycle, is that as you basically economically test a spec, they can refine the spec and actually commit to turning it into code only when the spec makes sense. So instead of doing a trillion interactions with developers that are probably more expensive, you just get the spec right, and after you're sure it makes economically sense, you develop it and you implement it. Okay, so as I said, quick prototyping capacity, speeds up stuff, and can be used into larger software stacks. Okay, so what is the main idea? In compositional game theory, we have some atomic building blocks. These are basically usually three things, and these are decision. Decision is strategic decision. So it means I observe something and I have to apply some strategy to do something. Then you have computation. Computation is like a non-strategic decision. It means you see something and you just compute something without doing anything else, without thinking basically strategically. Simple example is a function. And draw from nature is basically random parameters. So if I have to model, for instance, a game where at some point you need to flip a coin, that's where draw from nature comes in. You can basically, spit out a probability distribution of some sort to model these, non-deterministic behavior. And then you have two composition operations that are called sequential and parallel. So this is the main idea. This is our main building block. The open game is that thing there on the right. So the idea is that we have a process that, as you can see, looks a bit weird because it has like a forward direction from X to Y and a backward direction from R to S. So what is the idea? The idea is this game G observes something from the past. This is like the past and this is the future. It observes an X from the past, so the context provides an X to the game. At this point, the game has to decide how to act on this X. Again, this can be strategic, can be deterministic, but the idea is that the game says, okay, I saw X, I'm going to give you a Y. Now, the idea is that when you are giving the Y, you are sending the Y, quote unquote, into the future, your Y will have some consequences. The standard example that I'll show in the next slide is in Prisoner Dilemma. If I decide to, rat out my partner or not, this will have different consequences determined by a payout matrix. So the idea is you act on the environment with a Y, and the environment will reply with an R, saying R is the type of what happens, how the context reacts to what you are doing. and S, which is the quote-unquote magical wire that allows for the compositionality secret sauce we were talking about before, is basically, you can see it as the consequences, like, imagine that you have some context here that is giving you consequences to your actions. You yourself could be the context providing consequences for another game. So this is where S comes from. The idea is you do something, the context tells you something in return, and maybe you yourself have to, piggyback to someone else's before you. I will make an example in a bit, but the idea is that you can compose these things. So this is a standard composition. When Y and R match, you can glue these two games together. Again, the idea is G observes X, does Y. Now H observes Y, does Z. Some consequence Q comes to H. H in turn basically sends back some consequence type R, which becomes, R is basically the type of payoffs, for instance. So it becomes what G sees as a consequence of Y. So again, in this example, H is the context for G. G is doing Y. Now H observes Y and replies with R. Okay, so basically the idea is that you can compose these things, and when you do, you can obscure details in the middle and just represent this as a composite game. Then you have another kind of composition, which it's probably weird when you call it composition, but it's the parallel composition. So the idea now is these two games are not sharing anything. They are happening in parallel, and you are considering them at the same time. So when you do that, we say the composite game, for instance, observes something of type x1 and x2. Imagine that we are just drawing a box around these two things. You have two observation types, two inbound types from the past, x1 and x2. And that's why you bundle them together when you compose. Okay, so example. This is a prisoner dilemma in compositional game theory. You have two players. These two players do not observe anything. They just have to decide what they need to do. Betray or, do not confess. And then you have a payoff matrix, right? The payoff matrix basically observes the player's decision and spits out the payoffs. In compositional game theory, the whole prisoner dilemma can be captured by the composition of these three games. These two players are acting. You observes the actions and spits out the payoffs. So as I was saying before, the player one payoff is actually the magic wire into the past of the payoff matrix. And in this example, you can see that these two players will have strategic reasoning. They will have a set of things that they can do, and they will have to decide what to do. You will be fully deterministic. You will be a function. It will just observe the actions and deterministically spit out the payoffs. But then again, what if I want to change this? What if I want to make you into a player itself that can strategically decide what to do and what payoffs to distribute to the two players? Well, in this case, I can just change this piece and keeping these two pieces as they are. Or what if I want to represent the idea that actually player one observes what player two does before doing its action? Well, I will just have to change player one and copy this wire and fit it there. And now I have player two acts, player one observes this action and then acts itself. So you see, I can basically change things very modularly and compositionally without having to, level up my project and start again. Okay, so let me show you how all this stuff is actually implemented. So we have a DSL embedded in Haskell. The reason why we use Haskell is because, as I say, this thing was based on a kind of mathematical theory that is very deeply connected with type theory, and so using functional programming and programming language with a strong type system was mainly mandatory for us to be able to implement this thing without going completely crazy. I think that Jules can tell you a lot about this. It's freely available. If you go on our website, that is 20squares.xyz, you can just follow the GitHub link to the GitHub page. You can download this thing and play with it. And yeah, we used it for staking protocols, token design, order flow auctions, MEV-related business, and all this kind of stuff. So the idea is that in our DSL, we represent a game in this way. Literally what you see here. You have inputs, feedback, output, returns, which correspond to the wires in the picture, and then you fill the game with some internals. So, okay, these are the internals of the game. So if you expand the internals of G here, you will see this thing. So the first thing that you notice is that the inputs, feedback, output, and returns wires are duplicated. The reason why we do so will be evident in a bit. It's because, as I showed you here, this thing can be, for instance, bundled up into a unique box, right? So the idea is that this is exactly what's happening here. This is the outside box view where I only see the wires, but in the internals I can have more boxes interacting with each other. So this is why we duplicate the inputs so that we can represent the wiring. And then we have the operation that is basically the actual power horse of the thing. So operation, again, can be a dependent decision, so a strategic choice. It can be a function. It can be a draw from nature, or it can also be just another game. So I can basically fill this thing with a box that I defined somewhere else. So again, this is the example of the prisoner dilemma. As you can see, when you compose things, what you get is a box with no wires. That's basically a theorem that says that when your composition has no wires whatsoever, that's equivalent to a game in normal form. That is basically a game in the traditional game theory sense. So that's why you have no inputs, feedback, outputs, and returns wire. This whole block is representing this thing. Now, inside, you have these two things that are the two players. Again, they do not observe anything, and they have no feedback, but they have an operation that is dependent decision, and these two players have to choose between cooperate and defect, and they output this decision, y1 and y2, and their returns are their payoffs. And then you have the U box, which is this one. This one takes the two decisions output by the players. It applies a function, payoffs PD, that is basically your payoff matrix, and returns the payoffs as outgoing wires, basically. You can see that actually this thing is returning it as outputs, so it's spitting them up into the future and not into the past. The reason why we can do that, it's a technicality. That means we can always bend a wire. A wire that goes forward can always be bent into a U shape and be sent backwards. So that's why, basically, in a situation like that, like this one, the Open Games engine will automatically take care of the fact that these outputs must be piped into the corresponding returns. So there is some hidden magic that allows you to use this syntactic sugar. Okay, that's basically it. So now some of the things we are working on is we're working with the robust incentive and formal verification team from the Ethereum Foundation to actually interface this stuff with the Ethereum virtual machine, in particular with the HGVM, that is the implementation of the Ethereum virtual machine in Haskell that is being used by DAppTools, that is basically the, I would say, 0.1 version of Foundry for whoever uses that. And the idea is, by using this interfacing, as I told you, right, these boxes can be filled by strategic decisions, but also by functions. For instance, in this case, this thing here we say is a function. The idea is, with this integration, we will be able to take smart contracts, on-chain state, and all this kind of stuff, and plug it into a box. It will be a stupid box with no strategic content whatsoever, which is exactly what you expect from the Ethereum virtual machine. Like, you provide some input, and the Ethereum virtual machine spits some output deterministically. And then around it, you put strategic actors. So imagine that you want to model some kind of MEV situation. The idea is, in here you will have some smart contracts you care about. You feed it with a list of transactions that have to be executed in order. But now you can have another box before it, and you call it mempool, for instance, or you call it coordinator. And then after that, you provide the players, and now coordinator can strategically decide the ordering of these transactions to be fed to the EVM box. So again, the idea is that I can take contracts and that are non-strategic by definition, they're just stupid functions, but now I can embed them into a framework that allows me to reason strategically about them. So that's one of the things we are working on. We are also working on extending the analytics in a way that is, let's say, more intelligible, because at the moment, like, when you look at the analytics, basically the analytics of our framework, spit out either simulations or equilibrium conditions or stuff like that. But the output sometimes is very complicated, and we want to make it more manageable. And yeah, then we are also working on some extensions of the theory itself, of the engine itself, because there are things that are difficult that we can somehow do, but it's not clear yet how to do them in full generality. One example is repeated games. Repeated games are not super easy to do. You can simulate them using like Markov processes or stuff like that sometimes, but not always. Other things that we can do, I failed to mention, is that our engine is by default Bayesian. So you, by default, reason probabilistically. You can do mixed strategies, and basically, there are an example of mixed strategy is play this thing, option A 50% of the time, option B 50% of the time, for instance. And in that case, your expected outcome will be itself probabilistic in nature, basically. This is very useful in order flow auction simulations, which is one of the things that we are actively doing, and we will talk about them later on in another workshop, where the idea is we are not focusing on equilibria because they are too complicated to calculate. They are computationally unfeasible, but we are focusing on simulations. So the idea is I have some actors that are at some level in the MEV food chain, and they ask, how should I position myself in this order flow market? And what we are simulating is the expected outcome depending on what they do. So yeah, that's basically it. Yeah, I mean, we have 7 minutes, but we can show some code, but probably it's better to take some questions if someone has any.
This may be a stupid question, but from the point of view of if you have a compositional modules, and you keep adding compositional modules, is there any idea in the model of like attention degradation? So like if you, obviously you can have a game theoretically perfect game, but actually it's too complex for people to care about.
Okay, that is a really interesting question. So if I understand it correctly, I think that one of the kind of axioms of game theory that is somehow not so obvious is that players are rational, right? And if I understand correctly, what you're saying is that it's very difficult to stay rational when you are overwhelmed by information, or maybe there is an equilibrium to the game, there is some optimal strategy. Well, shit, it takes a trillion years to calculate, so you won't expect anyone to do so. Yeah, There are various ways to tackle this. One of them is by using modified utility functions, for instance, or modified observations. But by the way, I think this is exactly one of the reasons why we are focusing, as of late, way more on simulations than on equilibria. So I think order flow auctions are really a good example because auctions have been studied extensively in the literature. So basically, when you have a flavor of auction, you go in the literature and if equilibria for that auction have been worked out, probably you will find it in the literature. It's, I think, very difficult to find. I mean, there are, but a lot of auctions procedure have been worked out, and if they haven't been worked out, it's because it's unfeasible. There are some niches, but that's the state overall. But in order flow auctions, you have this recursive thing where you have multiple auctions taking place at the same time. It's a fucking mess, basically, and I don't think it's to be expected to have a simple way of calculating equilibria there. Sometimes you can be lucky enough, you can maybe apply like the revenue theorem or stuff like that and get away with it, but there will be cases where that's not possible. And that's why simulations are useful. In simulations, I'm not telling you if your strategy is optimal, I'm just telling you the expected outcome. So you could have a strategy worked out with some heuristics, and then you can basically see how much you stand to gain with that strategy.
Another small point about your question is that you have to assume you're not playing against people. I mean, there's tons of bots out there that run similar calculations to what we're modeling. So yeah, I mean, attention is relevant when you consider a game in which people play. But yeah, if you're running analytics, that's...
Thank you very much for the interesting presentation. Here on the right, on your left, actually. Yeah, hey. Here, on the left here. Thank you so much for the interesting presentation, the introduction to compositional game theory. I just wanted to ask, what is the assumption about the informational structure of the game? Do we have perfect information in order to compose those games, even backwards, and the feedback mechanisms to work? What does the system or the game or one instance of the system need to know about the other instances?
So, basically, the types here, the types of these wires can be anything you want. So in theory, they can really be anything you want. The way you model perfect or imperfect information is A, by hacking on the structure of the types, and B, hacking on the wiring of the diagram itself. So for instance, if I want to model, as I was saying before, a situation where player 1 knows player 2's action in this game before deciding itself, the way I would do it is by copying this wire, plugging it back as an observation to player 1, and taking this into account in the strategy, because now the strategy for player 1, dependent decision, will have an input that can be discarded. So player 1 can say, I don't really care, but can also be used. So in this sense, you can model games where some players have asymmetric information, they are aware of what other players do, they can actually lie. So you could also have that, player 2 has two different wires, one goes into U, the other one goes into P1, and basically this player is doing A, but is telling player 1 I did B. So you can model all these kind of things dynamically by changing the type structure and the wiring of the game. Sure.
Sorry, he was first.
Yeah, it's very unfortunate we didn't see a demo, but generally, does this formalism then actually suggest or even generate strategies for the players? Because, I mean, of course, if it's more like that you have a template, such as a mixed strategy with two options, then it's more like find me the parameters that maximize expected value, and that's cool. But like when you have a system that has a lot of players, then of course it's more like a Monte Carlo search in some parameter space type of thing. Okay.
There are basically 3 different modes in which you can use this thing. The first one is simulate. You give me a strategy and I tell you the payoffs. The second one is equilibrium verification. You give me a bunch of strategies and I tell you if that strategic tuple is an equilibrium or not. And the third one is equilibrium search. That is, I don't know anything, find an optimal strategy for me. Now, these things are ordered in how computational intensive they are. Equilibrium verification, I think, is linear. Equilibrium searching is like super exponential and horrible. And simulations are quite fast. Now, if you want to do equilibrium searching, which is just give me the strategies, the optimal strategies, that's where we are studying integrations with machine learning protocols, with machine learning techniques. I mean, you cannot escape mathematics. There are some theorems that tell you that there are corner cases with games that are horrible and you can't do anything about it. It will take the life of the universe to compute anything. But maybe you can have a very clever AI that tries to guess heuristically. You can use relaxed notion of equilibria like epsilon Nash equilibria where you are satisfied when you are epsilon close to an equilibrium. But another thing that you can do, and that's also very interesting, and then I think I'll wrap it up because we are going slightly out of time, is I can have a game with a parameter, okay? And I have an equilibrium strategy. That is usually a protocol designer has an idea of what is the equilibrium strategy with this parameter. Fantastic, we verify that that holds. Then we can start incrementing, decrementing, and tweaking that parameter until the equilibrium breaks. And what that does, it gives you the bound in which that strategy is optimal. So standard example would be stablecoin, some parameters related to the peg. When everything is as intended, optimal strategy for the player should be defend the peg. If it goes down, buy. If it goes up, sell. But then you start tweaking these parameters, and you can observe that domino effect when you say, okay, Luna is like USD is like 95 cents. I will go up, I'll buy. 93 cents, probably I'll buy. 85 cents, this thing is fucked. Drop everything. And then you have, this domino effect. So in this sense, you can try to quantify how solid an equilibrium is. And this is also computationally quite easy to do when you start with a known equilibrium strategy. So that's another way to use this stuff. Okay. Cheers. Yeah, sure.
You already started answering my question there. So this is a lot of very powerful, higher order, sort of like solutions capabilities. Mm-hmm. And what about at the lower level? Because I'm looking at this, obviously to explain it, you have to use a very simple example that we will get. But this looks like something I could script in Python. So at a lower level, are you just sort of like providing people with sort of like a clear framework for defining what each of these modules are?
Okay, so like our workflow is the following. As I said, everything is freely available, so you can just use it yourself. When we do, we call it economic audit because we don't have a better term for it. Basically, what we always provide is a report, but also the model. So you get all the code of everything. And this is very important, especially for projects like in Mevland. They have sensitive information, and like the fact they are giving you their real probability distributions or stuff like that, their secret sauce. So what we do is give us bogus data, no worries, as long as it seems sensible. We make up the model for you, and then you can run the analysis with the real data in-house. We don't have to know anything. You save your secret sauce, and everyone is happy. So yeah, you will always get the model code when we work. Absolutely, 100%.
Thank you very much. I think it's the lunch break, so bon appétit, messieurs.
Bon appétit.
So now the next one is in 45 minutes, right? At 1:25. Yeah. Okay, so see you around 1:20. I don't know.
1, yeah.